Hello everyone, this is an update to our effects system from the last video. Again, I'm Payman, this is Philip, my teammate.
Howdy.
We are from the spring of 2012 Embedded Systems class, University of Utah. So there are some updates to our project that we would like to share with you guys. So we decided to do multiple different videos. In this video, we're going to explain our software. So Philip is going to explain to us what DSP algorithms was used and what updates we have on those, and I will explain the control software for the embedded systems. So I'm going to pass it back to Philip and he will fill you up on what we have now.
Okay, so in our previous video, when we ended, we had a pretty good sounding distortion algorithm on the board. And as we experimented further with this, we noticed that if you let a single note ring and die out, at a certain threshold, the note appeared to be suddenly chopped off and died into nothing instantly. We found the source of the problem, and that was corrected by constantly polling how loud the signal currently is. And that unfortunately made the software so heavy that we were constantly missing samples, which drastically reduced the quality of the sound. We lightened up the code as much as we could. We currently were using a soft clipping function, which means you don't simply amplify and clip the signal, but in between you do a little bit of processing with an arctangent function to round the corners of that signal to give it more of a warm sound, more closely emulating the tube distortion of the analog system. We eliminated that, went back to hard clipping, and we were still unable to create a good quality sound given the limited resources of the board that would allow us to play the guitar softly and still maintain that distorted sound at an adequate level. So unfortunately we had to drop the distortion algorithm, went to distortion in hardware, which will be explained in a later video, and we got a couple other functions on there currently working. Delay works very well. We have a flanger which is working. The delay we had working in MATLAB code very well at the time of the last video. Unfortunately, the difficulty we're facing at that time was that MATLAB can look at an entire array and manipulate the array at will. Also with a very powerful processor. Our processor here is very limited as our resources. In order to introduce a delay in real time, it would be ideal to have an infinitely long array, which obviously is not possible. So what we did was we created an array which is adequately long to echo the sound of the guitar one time, and simply changed a little bit of the software behind the array to make the array circular, so that you have two pointers simply circling around in this array, one catching the signal, the other writing the signal to a different point in the array at a reduced magnitude. And then when you go back with a second pointer and pick that back up, throw it back into the original signal, creating the effect of an echo. And this we were able to repeat, so it sounds like the echo is repeating for all eternity, which makes it seem like we do have an infinitely long array. So that we were able to manipulate with limited resources and quite a bit of thinking. The flanger effect is going to alter the pitch of the sound, move that up and down. Ideally, we'd like to do that with a fast Fourier transform, which is actually a hardware chip embedded on the board. But because the board is so new and we have a very drastic lack of documentation, we are unable to actually access that chip at this time. We're hoping to be able to continue this project and get that chip working at some point. So the problem remained: how do you alter the pitch of the sound? We again utilized a circular array. This time, instead of just simply echoing, what we did was have a delay that's so slight your ear cannot actually detect it. And as the pointer circles around the array, we actually oscillate its position back and forth, which is in effect going to alter the pitch while that pointer moves around and oscillates. So that is working. However, it is eating up most of the resources in the board, so that one is occasionally missing samples currently. The quality is a little bit, takes a little bit of a hit, but it's not as drastic as the distortion function that we dropped. So I'll go ahead and turn the time back over to Peimon. He's going to explain more about the embedded systems software and how we actually use these signals.
All right. So as you can see, doing DSP algorithms is very tricky, and you're bound to not miss the timing deadlines and miss samples. So to explain a little bit of the control software, it's fairly simple, coming to that has a main loop that be running to check, basically reads the audio samples and checks on switches and checks on the knob that we have, that I'll be explaining in a minute. So it starts with the main function. It comes in, initializes the parts on the board that we are using, such as the board itself gets initialized, the I2C protocol to actually talk to the codecs to read the audio, the I2S to be able to send samples back and forth on the board. Basically the GPIO extension, so we could read in switches, and also one of the SAR ADC channels in order to read an analog knob. So after these get initialized, we enter our effects function, which is it starts by reading the switches. So unfortunately, the GPIO on the digital side is not interrupt driven. So we have a little bit of reading the GPIO line. It doesn't take too much time, so it works out having it in the main loop as the samples are being read. And then as soon as we read the switches, we pick up the sample. So we have a one I2S read, and now we have the sample, we know what switches, what control we want, meaning that are we engaging any of the effects, or are we just passing the sound through as clean. So it comes down and it starts checking the switches. So if one of the switches was selected, it will go and engage the first function, which is the delay. And it will pass the samples that are coming in to the delay function, and it gets saved into the array that Philip was talking about. And so if the other one was engaged, it will also read that for the flanger. Also, if we have, so those are the foot switches. Those are the switches that are on the ground. They're Marshall foot switch pedal, which will be shown in more detail in the next video. But those guys control the flanger and the effect inside of the software. So we wanted to read the knob, but here's the problem. The interrupt system that controls basically gives you an interrupt when the sample conversion is done, firing up too quickly, too often, and it was actually degrading the sound more than what we wanted, and we could not figure out why the interrupt is messing up work. So we ended up having to pull. Pulling the SAR ADC takes a lot of time, and it puts a damper on our timing. Therefore, you can't be reading the analog knob too often, meaning that we had to implement another switch that when that switch is on, the analog knob is checked, and when the switch is off, the very final value from its last time is preserved, and that's used until you engage it again and change the knob, and therefore you can have these range of values. And we're using the knob in order to change how much delay we have and how far the flange moves are far apart. Basically, the software calls a switch check function and then passes the signal to the functions that are for our effects. And so far, we got it to a point that we have a clean signal going in and out, and we're not degrading it too much. So in the next video, we will explain how the hardware is connected together and some sound samples. Thank you.